Hey there. This is a lecture for section 8.1, applications of the law of sines and the law of cosines. All right, we're just going to walk through several situations that involve non-right triangles, and some of them have right triangles as well. But most of these, I think all of these will require either the use of the law of sines or the law of cosines to solve. All right, say there's a surveyor wants to find the distance across a small lake, all right, with the surveying equipment. They figure out that they're standing 800 feet away from one side of the lake, 900 feet from the other side, at an angle of 70 degrees. All right, so then we could consider this a side angle side triangle, right? Because there's a side, an angle, and a side. The angle is enclosed between the two sides. All right, and I might, if you tried to solve this with the law of sines, you wouldn't be able to, right? We couldn't set up a ratio of an angle with its side across from it. So we have to use the law of cosines to solve here, right? So if we label this, maybe call this angle at 70 degrees alpha, so the side across from that would be A. We'll let 800 feet be side B, 900 feet be side C. Then the version of the law of cosines that we want to use here to find the length of A is going to be A squared equals B squared plus C squared minus 2 times B times C times the cosine of alpha. All right, so A squared then is going to equal, let's see, 800 squared plus 900 squared minus 2 times 800 times 900 times the cosine of 70 degrees. All right, put that all in the calculator and then take the square root, and we see that side A is going to be equal to 978.5 feet. Okay, it's a pretty straightforward application. I think it's a little more interesting though. Let's look at this next one. Here, in this application, the path of a satellite orbiting the Earth causes it to pass directly over two tracking stations, one labeled A, one over here labeled B, okay? And these two stations are 69 miles apart. All right, so let's go ahead and put that in. And look, we've now made a triangle that we can use to find things out. All right, so when the satellite is on one side of the two stations, the angles of elevation at A and B are given here. All right, so the angle of elevation for A is 83.9, the angle of elevation for B, 86.2. All right, so actually I think this is written in wrong. They should be switched. Doesn't matter. The diagram's what we're going to use. Okay, so how far is the satellite from station A? All right, so that's this distance here. We want to figure that out. We want to find out what that is. And how high is the satellite above the ground? All right, so how high is a satellite above the ground? We're going to have to drop a perpendicular here to find the height above the ground. All right, so we're kind of making a second triangle, aren't we? But we have a perpendicular that we dropped. And so the other thing we want to find is this height above the ground. All right, so that's what we're looking at. So we have several triangles that we can use here. I think let's go ahead and start with this obtuse non-right triangle. And I'm saying that because of the right triangle, I don't know anything other than this angle, and I can't solve anything in that right triangle until I find at least one of the legs, and I don't know any of them. I don't know the hypotenuse or either leg. All right, so let's go ahead and start with this obtuse triangle, and let's see if we can solve for both the missing sides, because one of the missing sides is that distance from station A, and then the other missing side will give us something to work with to find the height, if we deal with that second triangle, to find the height of the satellite. All right, so let me just blow up that obtuse triangle that we're going to work with here. We'll call it this guy here. All right, let's give it some angle measures. Maybe this guy will be alpha, this guy will be beta, this guy up here, we'll say he's, not lambda, we want to say gamma, don't we? gamma. So then this guy C, alpha, is across from A, and beta is across from B. All right, so there's a triangle with our standardized labeling. Okay, we know this angle here, we know that it's 83.9 degrees. All right, we know the length of side C is 69 degrees. Those are the givens. All right, so is there any way that I could find B or A when I only know one angle on one side? No, I need more givens than that. So we have to figure out, is there a way that I could find one more thing, one more aspect of this triangle, find another angle or another length of the side so that I can solve for A and B? Angles are usually easier. And look at this. We know this angle here is 86, right? So if I were to extend this, right, I could say that this angle here is 86.2 degrees, right? Well, since angle beta right here is supplementary with this 86.2 degrees, okay, I could then say that beta, let's put an arrow to it, I can then say that beta is 180 minus 86.2 degrees, okay, and that would be 93.8, excuse me. 93.8 degrees. All right, so now we know two angles, and again, we have an angle side angle triangle. Well, not again, we have an angle side angle triangle. So I could find this third angle up here, gamma, and use the law of sines, right? So let's find out what that angle is. That angle, since the interior angles of a triangle always add to 180 degrees, I can say that gamma is 180 minus the given angle, 83.9, minus that other angle we just found, 93.8, and that is 2.3 degrees. All right, now we know all the angles, so it won't be that hard. To find B and A. Let's go for B first. I think we'll use the law of sines here because we have a side and its opposing angle. So we can say that the sine of 2.3 degrees over 69 is equal to, let's go for B first. So that would be equal to the sine of 93.8 over B. All right, if we do cross products here, we can say that B times the sine of 2.3 is equal to 69 times the sine of 93.8. Then divide both sides by the sine of 2.3. So B is going to be 69 times the sine of 93.8 divided by the sine of 2.3. And putting in the calculator, we see that B is 1,715.6. What are we doing here? We're doing miles, right? Miles. All right, so that's the first thing that we needed to find. That's the first thing that we needed to find. Now the second thing is the distance of the satellite from above the ground. All right, so at this point, I have to switch triangles. Okay, I have to switch triangles, but I don't know enough about this right triangle. So let me see if I can find this missing piece here. And we'll make that purple. If we can find that missing piece there, right, that's going to be the same as side A of that obtuse triangle. All right, then I'll have enough information to work with that right triangle. All right, so A, I can use the law of sines again to find A. Okay, A is going to be, we'll say the sine of alpha, which is 83.9 over A, is going to be equal to, we'll use the ratio with C and gamma again. It'd be the sine of 2.3 over 69. All right, cross products and division will give us, our solution for A. Let's see, it's going to be 69 times the sine of 83.9 divided by the sine of 2.3, which, when I put that in the calculator, is 1,709.6. All right, so now, let's stick that in there, 1,709.6. Now I know the length of the hypotenuse in this little right triangle. Okay, I know the length of this angle here, or I know the measure of this angle here. It's 86.2. What I'm looking for is the height up over here. Maybe we'll call that, let's switch to red, I guess. We'll call that H. All right, so to find H, I could use, I could just use the definition of the sine, right? And from SOHCAHTOA, right? Because the sine is equal to the opposite over the hypotenuse. And for this angle beta here that I know, it's equal to H over 1709.6, right? So I could then say that the sine of 86.2 is equal to H over 1,709.6, multiplying both sides by 1,709.6 gives us H times the sine of 86.2. I'm putting that in the calculator. We see that that height is 1,705.8. All right, and that was the second piece of information we were looking for. Okay, let's look at another example. Okay, here's one. We have a 113-foot tower. There it is. Okay, that 113-foot tower, it's located on a hill that is inclined 34 degrees to the horizontal. Okay, a guy wire is attached to the top of the tower and anchored at a point 98 feet up the hill, okay, from the base of the tower. Okay, we need to find the length of this wire right here. So that's what we're looking for. There's that piece there. All right, so we got a triangle that we can work with, right? Tower could be one leg. There's a triangle. What do we know about that triangle? Well, the only thing we know about it is the length of two of the sides. It's not enough. Not enough to solve it. All right, so what do we do here? Let's see. Well, since we know that hill is 34 degrees to the horizontal, I could sketch a parallel line right here, or another horizontal line, like that, right? And then if this angle is 34 degrees, then I know that this angle here also has to be 34 degrees since these are parallel lines. Looks like 340, doesn't it? Since they're parallel lines. And this angle here, look, this would be a right angle, all of them together. Here, let's sketch this out a little bit better here. All right, so this angle here is 34 degrees. Since we have a right angle with the horizontal, then I know that this angle here, that one, has to be 90 minus 34, or 56 degrees. All right, so that gives me something else that I can work with then, right? All right, so I know the height of the tower, that's 113. I know how far up the hill that wire needs to be attached. That's 98. So now look, I have a side angle, side triangle. I could use the law of cosines to solve this. All right, sines won't work because I don't have a ratio that I form. With the law of cosines, let's see, if I call this side up here A and this angle that's 56 degrees over here alpha, right, have B and C, we could say B was 113 and C was 98, so I can use the version of the law of cosines. A squared equals B squared plus C squared minus 2BC times the cosine of alpha. Plugging in our values here, we have that a squared will equal 113 squared plus 98 squared minus 2 times 113 times 98 times the cosine times cosine of 56 degrees. Okay, and then plugging into the calculator, then taking the square root of it, we see that A is equal to 99.9 feet. All right, let's check out another one. Let's climb here. Here we have like it's flying over a straight highway. Here's the highway plane. The pilot determines that the angle of depression to two mileposts, 4.3 kilometers apart. All right, so here's our 2 mileposts, A and B. They're 4.3 kilometers apart, so I can put that measure in, right? And then the angles to depression are 32 degrees and 56 degrees, as shown here. All right, we want to find the distance of the plane from point A. All right, so we're looking for that. And also the elevation of the plane. Oh, this is similar to that other one we did, right? So we'll have to drop a perpendicular here to find the elevation of the plane, how high the plane is. Okay, so we're also looking for that leg there. All right, so that's what's going on. We've got a nice little right triangle that has the two of the things that we're looking for. However, we don't know the measures of anything in that triangle. None of them were given. None of them are given. Right away, I can see since this is a right angle here, all right, I can see that this angle here, but it's complementary with this 56-degree angle. So this angle here, we could say, is 90 minus 56. Right? 90 minus 56, which is 34 degrees. All right, so we know one angle here, but we don't know any of these lengths of any of the sides, right? We've got to have at least one length of something here to solve that. I could find this angle here. Let's see, where do I want to go next with this? Well, there is another triangle, that I could work with here. Let's make it in red. Look, there's this triangle here. Maybe this one could be helpful to us, the red triangle, because I know some of the measures, right? Or at least I can find them, right? So if I blow this triangle up just to make a little bit more room to write, pull it out. That's that obtuse red triangle there. I can determine what this angle is, right? Because these two together are 56, right? So this little angle here is going to have to be 56 minus 32. Right, since this angle is 32 and the whole thing is 56, this other little angle, that's going to have to be 56 minus 32, right, or 24 degrees. All right, so we know one of the angles now. We've got that. We actually have one of the sides that was given between A and B. We're going to call that angle there alpha and that angle there beta, right? So this side length is 4.3. That's alpha and that's beta. This angle up here will have to be gamma. And across from gamma is going to be C. So that'll be our 4.3. We don't know A and we don't know B. B would be very nice to find though, wouldn't it? All right, well, what do we have to work with here? We only have one angle on one side. It's not enough. We've got to come up with another angle, right? We've got to come up with another angle or another side. All right, I don't see anything that's going to lead to another side, but we might be able to come up with another angle. All right, so here's what we can tell. Since there's parallel lines here, opposite interior angles on parallel lines are equal. Remember that from geometry? So then I could say, why is that not working? My eraser is just sometimes not working. There, got it to work. All right, so then we could say that this angle here is 56 degrees. It's got to be the same, right? Because see, we have parallel lines, and these are alternate interior angles, so they have to be the same. So if this is 56 degrees, then this angle over here has to be 180 minus 56, because those are supplementary angles, right? So that gives us the measure of angle alpha. 180 minus 56 is 124. Right? So now we have two angles and a side. All right. Since we have an angle side triangle, I'll be able to use the law of sines here, right? Because I can set up a ratio, gamma, sine of gamma over c. So let's use, let's go ahead and use the law of sines. We are going to need this third angle though. Not hard. That's going to be what, 180 minus 124 minus 24, which is 32. All right, so now we have all the angles. We're good to go. Let's use the law of sines and see if we can find the length of B, which of course is the same as this guy here. We need that. All right, so we can say that the sine of alpha, which is 124 over A. No, you know what? I don't want alpha. What am I saying? I want beta because I'm looking for B, right? So I want to say the sine of beta, which is 32, over B equals, and the ratio that's known that we have here now is sine of gamma over C. So that'll be the sine of 24 over C, which is 4.3. Here we go. All right, so now cross products and division by the sine of 24 will give us B. Putting that in the calculator, we get 5.6. Okay, well good, we just found one of the things, right? We found the distance from the plane to point A, right? That was 5.6. Now we need to find the altitude of the plane, or how high that it is. All right, so let's redraw, oops. Let's pull out that right triangle, see if we can work with that. Okay, here's our right triangle. We found that angle up here was 34 degrees. All right, and now we just found the hypotenuse of that triangle because it's the same as side B, right? That hypotenuse is 5.6. What are we looking for? We're looking for the height. Maybe we'll call it H. Can we find it? Do we have enough? Yes, I think we do, because if we use the cosine of 34 degrees, right, we can say that since cosine is equal to adjacent over hypotenuse, the definition of the cosine, we can say that the cosine of 34 degrees is equal to h over 5.6. So h then is going to be 5.6 times the cosine of 34 degrees. You know that, I'm going to have to look that up real quick on my calculator. Let's see what that is. 5.6, oops. 5.6 times the cosine of 34. And there we have it as 4.64. Yeah, we'll take 2 decimals on that because I don't like to round with 4s. Okay, so 4.64. And what are our units again? Gosh, kilometers. Okay. Let's just look at 2 more examples here. All right, here's one involving 2 planes. All right, they're leaving the same airport at the same time. All right, they're leaving the same airport at the same time. All right, one flies 20 degrees east of north at 500 miles per hour. All right, let's say this is the airport. Okay. And if a plane is flying 20 degrees east of north, let's see, north and south would do this. Right, there's our north and our south, we'll say. There's north, there's south. 20 degrees east of north is about right there. All right. And then the second flies 30 degrees east of south. Okay, so 30 degrees east of south, there, would look something like that. All right, so now it looks like I have a triangle that I could form. Here it is. I might be able to work with that triangle to answer some questions. All right, what is it that we need to know? We need to know how far apart are the planes after 2 hours. Okay, how far apart after 2 hours? After 2 hours. So how far have these planes flown in 2 hours? Well, the one that's flying 20 degrees east of north was flying at 500 miles per hour, right? So that's just going to be 500 times 2, or 1,000 miles, right? The one that's flying 30 degrees east of south is flying faster. It's flying at 600 miles per hour for 2 hours. So its total distance is going to be 1,200 miles. So we know the length of 2 of these legs of this triangle. We're looking for the length of the third leg. Call it A. Okay. We need more than the lengths of 2 legs, but we can determine one of the angles here. Look, these 3 angles, like if I think this angle here inside the triangle, these 3 angles are complementary, right? Since they're complementary, then I know that this interior angle is going to be 180 minus 20 minus 30, 180 minus 50. That's going to be a 130-degree angle. Okay. Knowing that I have now a side angle side triangle, I could use the law of cosines. If we called this angle here alpha, again, I could say that a squared is equal to b squared plus c squared minus 2bc times the cosine of alpha. So a squared is going to be, which one should be b? We'll say this is b over here. We'll say this guy is c up there. So this is going to be 1,200 squared plus 1,000 squared minus 2 times 1,200 times 1,000 times the cosine of that angle, 130 degrees. Okay, plug all that in the calculator and take the square root of it. And we see that this length of side A here is 1,995.7 miles. All right, one more. Let's go one more. Let's look at this guy. We have 4 sequential sides of a quadrilateral. It's hard to say. 4 sequential sides of a quadrilateral that have lengths of 4.5 centimeters, 7.9 centimeters, 9.4 centimeters, and 12.9 centimeters. Okay, we also know that the angle between the 2 smallest sides is 117. We need to figure out what is the area of the quadrilateral. Boy, this is a long one. All right, let's see what we can do. Let's draw a sketch first to start with. Okay, I'm going to let this be the side that's 4.5 centimeters. I'm going to let this be the side that's 7.9 centimeters. So then the angle in between them is 117. Okay, then we have 2 more sides. One is 9.4. So we'll let this be the side that's 9.4, and then this will be the largest side, 12.9. There's a little diagram that we can work with. All right, so we have this really weird shaped quadrilateral, and we don't really have any tools available to us for finding things out about quadrilaterals. We don't even have a formula for the area of a weird shaped quadrilateral like this. So we're going to need to divide this up into different shapes. Since we've been working with triangles, let's divide this up into some triangles. All right, I'm going to draw a line here and make this quadrilateral be two triangles. Reason I'm doing that is because I know this angle, and then that's going to make this top triangle easier to work with. Okay, so the approach that I think we need to take here is find the area of the top triangle, the area of the bottom triangle, and add them together. Right? Now the formula for the area of a triangle is 1/2 times the base times the height of the triangle. Right? So we are going to need to find the base of the triangle and the height of the triangle. Now, we could call this side here the base of the triangle. Let's do that. Let's call that the base of the triangle, because then we'll be able to use it in this triangle over here as well. And we can find that value, can't we? We could find that value. Actually, oh, there's my eraser not wanting to work again. I think the battery or something funky is going on with my pen. Maybe I accidentally changed a setting without realizing that I did it. But I'm dead in the water without being able to erase. Let's see. There. Sometimes when I write and then erase, nope, not even that's working out. All right, well, we may have to continue this with stray marks all over since I can't seem to get rid of them. Ooh, it worked. See if I carry what I tried to erase here. This was a mess. There we go. It worked. All right, I wanted to move that over and call this the base over here because I got a reason for that. All right, let's find that base. Side angle, side triangle. So let's use the law of cosines, right? We'll call this angle up here beta. Side across from it's going to be b. So we can then say that b squared equals a squared plus c squared minus 2ac times the cosine of 117. Oh no, a beta, and then we'll put in, I'm losing my eraser again. Oh my goodness. There, got it. Beta. Okay, let's put our values in. So b squared, we'll say 4.5. No, we'll say this is our A, and this is our C. Oops, did it again. Now I gotta erase. Oh. Okay. That guy's our C. So A squared, that's 7.9 squared plus 4.5 squared minus 2 times 7.9 times 4.5 times the cosine of 117. All right, the cosine of 117. So, well, we don't have these values, so let me calculate that real quick. Oh, I lost my calculator. 1 second. I think I'm going to switch over to my good old-fashioned trusty TI-84 handheld because I think my computer needs a reboot. I think that's why everything isn't working. Oh no, now the batteries are dead on mine. This isn't even Monday and I feel like I'm having one. All right. Gonna have to use the software. And somehow it got closed. So let's find it again. And there it is. Start it up. Okay. Let's see what that's gonna be. 7.9 squared plus 4.5 squared minus 2 times 7.9 times 4.5 times the cosine of 117. All right, 114, but I want to take the square root of that. And we find that B, after all of that, we find that B is equal to 10.7. All right, so now we know what's going to be the base of the two triangles, but we still have to find out the height, right? The height of the triangles. So how are we going to do that? Well, we just made a right triangle, didn't we? So we might be able to use that. Okay. Also, we have some other things that we can use. Oh, yeah, we can. Now that we know this length, we can find any of the angles down here using side, side, side. All right. So which of these right triangles should we use? It doesn't really matter. It doesn't really matter at all, as long as we have an angle that we can deal with. So the angle that we might choose to do, we'd either need this guy or we would need this guy, okay? And since we have both of these two sides, I'll probably go ahead and find that. Okay, battery just completely died on my pen. It will not write. Well, you know what we're going to do? We're just going to stop this lecture at this point. And here, you guys will like this. Here's an opportunity for extra credit. All right, finish solving this, snap a picture of it, send it to me, and I'll give you a couple extra points on the test. Okay? Enjoy. And this is going to have to end the lecture because my pen just died.